And welcome back. As we go ahead and dive into more facets of our own solar system, let's go ahead and take a look at planetary rings. So when we start talking about planetary ring structures, what are we referring to? Obviously, the first thing that might pop in your mind is rings such as those you might find around Saturn. But in addition to their moons, all four of the giant planets in our solar system have rings, with each ring system consisting of billions of small particles, or moonlets as they are often referred to, orbiting close to the planet. Now note that rings are not unique to the giants, but have been discovered around dwarf planets as well. Now each of these rings displays a complicated structure that is related to the interactions between the ring particles and the larger moons. However, the four ring systems are very different from each other in mass, structure, and composition. So what are those differences that we find in the ring structures around our four giant planets? Well, Saturn's large ring system is made up of icy particles spread out into several vast flat rings containing a great deal of fine structure. The Uranus and Neptune ring systems, on the other hand, consist of dark particles combined to a few narrow rings with broad empty gaps in between. Jupiter's ring and at least one of Saturn's rings are merely transient dust bands, constantly renewed by dust grains eroded from their smaller moons. So, with that in mind, we can beg the question, what exactly are rings? How do they come about? What is the more fine minutiae we might wonder about making these different from one another? Well, a ring is by definition a collection of vast number of particles following its own orbit around the planet. Therefore, when we start looking at this, we can argue that the inner particles in a ring system revolve faster than those farther out, and the ring as a whole does not rotate as a solid body. Instead, the ring particles are independent. So if we took those individual ring particles and we made them widely spaced, they would move independently, pretty much like separate little moonlets. Like if we took each one, separated out to think of it like its own moon, each one would have its own orbit. The ring is not a solid disk that spins around the planet. In the main rings of Saturn and Uranus, the particles are actually close enough to exert mutual gravitational influence, and they occasionally even rub together or bounce off each other in low-speed collisions. Now, because of these interactions, we see phenomena such as waves that can actually move across the rings because, again, of the density of the particles in those ring systems. So what causes the rings? Well, there are two basic ideas of how such rings kind of came to be around our gas giants. The first is the breakup hypothesis, which suggests that the rings are the remnants of a shattered moon. Or, you might have something like, for example, a passing comet, or maybe an asteroid might have collided with the moon, breaking into pieces, and then tidal forces then pulled those fragments apart, and then they therefore dispersed out into a disk. The second hypothesis, which takes the reverse perspective, suggests that the rings are made of particles that were unable to come together to form a moon in the first place. So there wasn't enough gravitational density for those particles to really coalesce into a moon. In either theory, though, the gravity of the planet plays a very important role. So let's start exploring this through the rings of Saturn. The three brightest rings of Saturn are labeled with the names of A, B, and C rings. The B ring is, of course, our brightest ring, easy way to remember, B is for bright, and has the most closely packed particles, whereas the A and C rings are more translucent. Now, the total mass of the B ring, which is probably close to the mass of the entire ring system, is about equal to that of an icy moon, 250 kilometers in diameter. Now, between the A and B rings is a wide gap, which we refer to as the Cassini division. Now, Saturn's rings are very broad, and we obviously can see them, it's one of its defining features, but they're also very thin. The width of the main rings is 70,000 kilometers across, yet their average thickness is only 20 meters, a distance that you could easily walk yourself, and you would traverse the whole breadth of that ring if you were to try to walk it from top to bottom. The ring particles themselves are composed primarily of water ice, and they range from grains the size of sand all the way up to house-sized boulders. Now, what about the other rings around Saturn? Because there are other ring systems besides the A, B, and C ring. Well, Saturn has a few narrow rings less than 100 kilometers wide, the most prominent being referred to as the F ring. Now, Saturn's narrow rings resemble much more closely the ring makeup that we would see around Uranus and Neptune. There's also a very faint tenuous ring, which we refer to as the E ring, associated with Saturn's small icy moon, Enceladus. Easy way to remember that one, E-ring refers to that moon. Now the particles in the E-ring are very small and are composed of water ice. Since such a cloud of ice crystals has a tendency to dissipate, the ongoing existence of the E-ring strongly suggests that it is actually being continually replenished. Now, with that being said, let's look at our next set of rings, which is the rings of Uranus. Now, Uranus's rings are narrow and black, making them almost invisible from Earth, which is why often when you look at Uranus, the depictions, you don't necessarily see the ring system around it. The 9 main rings that are part of Uranus were discovered in 1977 from observations made of a star as Uranus passed in front of it. Astronomers expected the star's light to disappear as the planet moved across it, but the star actually dimmed briefly several times before Uranus reached it, as each narrow ring passed between the star and the telescope. Voyager then studied the rings and identified 2 more when approached in 1986. Now, the outermost and most massive of Uranus's rings is called the Epsilon ring. It's only about 100 kilometers wide and probably no more than 100 meters thick. The Epsilon ring encircles Uranus at a distance of about 51,000 kilometers, about twice the radius of Uranus, and contains about as much mass as all of Uranus's other 10 rings combined. Now, the individual particles in the Uranian rings appear to be primarily carbon and hydrocarbon compounds. Organic material of this sort is actually rather common as we look at the outer solar system. Many of the asteroids and comets are also composed of dark tar-like materials. Now, in the case of Uranus, its 10 small inner moons might have a similar composition, suggesting that one or more moons might have broken up at some point to actually make these rings. Now, what about Neptune? Because we said all the giants have rings, so let's look at Neptune. Well, Neptune's rings are generally pretty similar to that of Uranus, but they're even more tenuous. Now, there's only 4 rings around Neptune, and the particles here are not as uniformly distributed along their lengths. Now, because these rings are so difficult to investigate from Earth, it's actually going to be a very long time before we understand them very well, because remember, Neptune is a very, very far distance away. So let's put a pause on this and start talking about the interactions between rings and moons, because you remember a lot of the giants also have a very large moon system. And so when you have something like moon systems that are in play, how does it affect these rings that are orbiting the planets? Well, most of the gaps in Saturn's rings, and also the location of the outer edge of the A ring, result from the gravitational resonances with these small inner moons. Now, resonance takes place when 2 objects have orbital periods that are exact ratios of each other, such as 1 to 2 or 2 to 3. The largest features in the rings of Saturn are produced by the gravitational resonances with the inner moons, while much of the fine structure is actually caused by the smaller embedded moons.